My name is Huda Nassar. I'm very happy to be here today in a Python conference. I hope when I first came here, I felt like an intruder, but then everyone told me it's an open space and a free space, so I hope I'm not going to intrude on the Python lovers, whom you are, I'm guessing, with material. First of all, just to know, so that I know my as well, how many of you have experienced Julia before or have at least played around with it? Just maybe 2 or 3. Okay, that's fine. That's actually great. We can go over the basics and see the details from the very beginning. So just so that you know where we're headed today, there's a link for the code that is provided online, so please feel free to follow along. At this point, I guess my recommendation would be just to locate that URL. You don't have to clone or download the repo yet. I'll tell you what we're going to do with it in less than 10 minutes. I'll first try to get your attention on how we're going to do these 2 hours. First of all, we're going to go over the first 3 components, which are a Julia description and then some Julia features, and we're going to do basic wrappers. So we're going to take simple Python code and simple C++ code and try to wrap them into Julia. Then we'll break for 15 minutes and come back, do some more complicated stuff with not really complicated, just more complex wrappers, taking existing packages online, which are C packages and Python packages, and then we'll end with some statistics and machine learning tools in Julia. So to start with, I will first... Okay, this is very small. We're going to do it together over an iJulia notebook. First of all, I'm going to go over just the introduction of the Julia statement and show you some very few examples, maybe 3 or 4 examples of why Julia language. This is really just copied and pasted from Julia's website. I'm just going to go over this phrase by phrase and take one phrase and say, why is this the case? First of all, it says that Julia is a high-level high-performance dynamic programming language with technical computing with syntax that is very similar to people who program in Python, R, or MATLAB. So this is just to tell you, don't be scared. The syntax is really so simple and easy. It's very similar to things you've been doing in Python. This is A is equal to 1 plus 1. This is a string, and this is how we're printing a string. This is really just basic syntax. Sophisticated compiler, there are so many ways to promote or say, oh, is it too small? Okay, thanks. Is this better? Okay. The second statement is sophisticated compiler. I know there are so many ways to promote or say why Julia has a sophisticated compiler, what goes in. But here's just a sneak peek, or here's just a very small, tiny example. For example, this is a function that only simply takes in a value x and tries to square the value x. A really fun tool in Julia tells you or allows you to find the square value of 1 and try to get the LLVM code of this function. So if you run this code, what you'll see, first of all, I'm going to comment these, run again. So code LLVM of my square of 1. What happens is that it shows you the LLVM code, and it tells you there's a multiplication happening where the number is an integer of type 64, represented with 64 bits. When you run it with a 1.0, which is a double, it tells you that we used a different multiplication, which is the fmul, and now it's using a double. So this is just to tell you, okay, we can see these things. The really nice thing is that the Julia compiler, for example, if we run another function and call it my other square and tell it that, we'll go over the syntax in a bit, but this is really just a sneak peek. And we tell it here that the type that we're using is a real or anything less than a real, and this includes floats, integers, and floats and integers represented in different bits. There's more. If it is of type real, then we can square it. What happens is that, again, we're going to run the LLVM code and see that the same things happened. There was a multiplication and a F multiplication. There was an I64, which is an integer 64, and a double. But what really happened is that the second function sorry, there was something. Okay, yeah, I guess if you run this. Okay, this was unexpected. There's something wrong with my computer right now. It's running more things, but usually the my other square should take less time because we've already told the compiler what is the type of the input. Well, on average, it's taking at least as bad as the first function, but it's always less than it's taking less time than the previous function. So the point here is that in Julia we can tell the function what is the type, and that way the compiler will not need to guess or to find out what is the type of the function it's going to use to multiply a value by another value. It's going to know the function to be used automatically because the type is going to be passed. So again, the point here is if we want to say let's write generic Julia code and give it to the compiler to run and compute, it's not as easy or simple as it is. You can Okay, we're getting a battery, so should we wait or? Okay, so the point here is that we can't just write generic code and give it to the Julia compiler and say, okay, just do whatever you want. There are things that the user can do to make, when performance is an issue, the user can affect and make the code run much faster. This is also a sneak peek onto what distributed parallel computing can do in Julia, or how we can do it. There are multiple ways to do this, but this is just an example. So if we add some processes here, we can, so basically here we added 4, and we can define a function by just this at everywhere macro. So we send this function, which is the my other square. We say, let every processor know what this function is, and then we take, so if v is the values between 1 and 100, it's a vector of all 1 through 100, we can send the value v to all the processors via this function pmap. And since all the processors know the function my other square, it's going to be able to run all of these in parallel. So parallelization could be as simple as this. Numerical accuracy, here's just a small example as well. If we have x and y, and x is 2.15 times 10 to the power 12, and we have 1.25 times 10 to the minus 5, if we just run the regular x minus y, this will show us 2.15 times 10 to the 12, which is exactly equal to the value of x, because y is really very tiny compared to x. But if we care about some more accuracy, we can use this big float function, which represents the numbers we want with higher precision. You can actually set big float precision. So you can set the big float precision to be as many bits as you want, and this will give you even just a bigger number, or a number represented with a bigger number of bits. And now if you find the x minus y, it's going to be a different value, but it's going to be using more bits. If we use 256, it's going to be a little bit smaller, but that's how you can change precision. There are things that I'm going to skip from these notebooks just for the sake of time, because we have 2 hours, and I think what I have here is material for more than 2 hours. So, but this is an example for you. Again, this is not really numerical accuracy, but this is just an example that can show you things you could do for your Julia code to make it run faster. And in this case, there's a constant, which is C, which is an integer, and a compiler would want to compute the integer summation together, and then compute the integer plus float, if we have a float here, rather than computing float plus integer and then float plus integer. So you can use this really nice macro called the fast math macro. What it does essentially is that if you have a summation of different types, what it does is that it groups the same types together, sums them together first, and then do the summations of different types, rather than this sequential way of doing float plus integer and then float plus another integer. This is just to point it out. You can experiment with it. This is what it essentially does. It puts parentheses in the right places. There's a much more extensive mathematical library, the standard library. You can find it here. And I know that I can't go over all the details here. This very first notebook, the reason I put it there is just to tell you, okay, there are these bits and pieces of everything. There's much more into every of these things. Okay, so now I want you to actually use this code and download this code and play around with it. So to get started with Julia, first of all, everything we're going to be doing in today's session is going to be based on Julia 0.4.6. The current release, the current stable release is 0.4.6. The nightly releases, if you really want to play around with the most up-to-date, the code might have changed just last night, for example. You probably wrote something and you come back and say, let's try it, and it might not work or whatever. If you are that adventurous, you can go try the nightly builds. There are so many things that are different, and there are so many fun things coming from in the coming versions. But what we'll use today is 0.4.6. To Julia's goal, again, the goal is performance. If you want to write really simple code, you want that simple code to be running as fast as, hopefully, write code like Python and let it run like C. Be able to access libraries that are the basic Julia libraries. They're open source. Everyone can view them. Everyone can go see them, and everyone can go update them if they want to. Where we're going to run Julia from today. So there are multiple options. There's first of all the Julia box, which I'm going to show you what we're going to do with it in a second. Whoever wants to do the command line interface, it's really very simple. If you go to the downloads page of Julia, you can download, depending on your system, you can download the configuration you need and just open it and use it. There's also an IDE, if you prefer to use an IDE, it's called Juno Atom. But I would really appreciate if we all use today Julia box. And the way we do it is really simple. If we just click on this link, if we are all on the GitHub repo, you go to Julia box. You have to sign in via your Gmail or GitHub or LinkedIn account. If you are okay with agreeing on the terms and conditions, which would be great. Again, anyone didn't follow on what the link was, it's juliabox.com. Sorry, it was .org. Once you've signed in, all you have to do is clone the repo from the sync command. So if you go to sync, which is the fourth tab here, and go get the link and add it. Okay, so okay, it worked. Did anyone try to do it and didn't work? It's not working. Sure. Okay, I'll do it again. So you go to juliabox.org, .com. Sorry, I keep saying .org. It was .org. So this is the website you want to go to, juliabox.com. And then you want to go to the Sync tab. Okay, that's fine. Anyone else experiencing trouble, or I'll come ahead. Yeah, put it here. And then add. It's not responding. Trying with Google. Okay. Anyone else needs help setting up? Okay. So can you try again, refresh? Okay, if you're having trouble with Julia, try juliabox.org. So juliabox.org. Yeah, you have to log in with one of these. Ah. So JuliaBox is one way to be used. The other way could be downloading Julia from the downloads page and just using it as a terminal command. So what you'll see is something like this. This is working. Good. So if people are interested in using notebooks, what they can do from the terminal is do package.add iJulia, which I already have it added, so I don't want to add it. But and then you can use and then you can type in using iJulia and then notebook, and that will also take you to a local notebook on your computer. Okay, I think. Does anyone else need help with setting anything up? Okay. Then we'll proceed with the steps that were written here. So notebook number 2 here with the getting started is really just for you to be able to set up Julia on your own computer. If you want to set up things locally, you can use a Jupyter notebook by adding the iJulia. Or if you want to set something up on the cloud, there's the JuliaBox website. It could be juliabox.org or juliabox.com. Each of these should work fine. I don't know why they're not working today, or maybe, I don't know, I really don't know the reason, but it should work. Sorry. Were you trying to get a picture of this one? Okay. So now I'm moving to the first folder on the GitHub repo. That's where we started from in the warm-up. If we go to notebook, that's what we're going to be doing now. So here, what we're trying to see or show you is really the syntaxes. Sometimes there's a very similar syntax that produces a different thing. So this is just going over very basic syntax of Julia. So this is a string. So this is a string. You can, like Python, you can start it with a three quotations to, if you have a quotation inside the string. So that's how you do it. This is the bitwise operators of AND. So it's really just simple. This is a vector. That's how you define it. There are things like the modulus or dividing. There's a very interesting difference between the slash and the div. So if you want to divide m, which is of value 8, by 2, it's always going to return a double. And types are really important in Julia, and you have to be careful with them. But if you always know that the result of this division has to be an integer, and you want to use it for indexing a vector, let's say, you always want to use the div operation, because div returns an integer. So the difference here between m by 2 and div m2 is that this has a type double, and this has a type, or specifically this has a type float 64, and this has a type int 64. So floats and integers. This is a basic if statement. Unlike Python, Julia code has an end keyword after an if statement, or other things we're going to see now. This is an if statement. We printed something if a is bigger than 1. Scope is really important in Julia. Scope is real. So if we have an internal value, we call it's 100, and then we say we do a for loop from I is equal to 1 through a, and this really just means it's the range of 1 to a in Python. And update the internal value. This is going to change the internal value to 10. But if you define a real internal value inside a for loop, it's going to complain and say this is undefined. So if you want to be able to access a value after a for loop, you have to define the value before the for loop. If you define it in the for loop, it remains in the scope of the for loop. It doesn't remain in the scope of the program. This is interesting because it could be a very similar syntax to Python, but it's not really a similar behavior. So in Python, if you do a list of 1, and then 2, 3 in brackets, that's understood as a list of 1 as one entity and 2 and 3 as another entity. But in this case, if you do something similar in Julia, what it really just does is that it concatenates or puts all of them together in one vector. So if we compile this or run this, we're going to see that the vector is just the 1, 2, 3 values. There's no distinction. If you really want to get a behavior that is similar to Python, this is what you will do. You will have to precede the square brackets by the keyword any. So the point here is there are things that are very similar in syntax but behave differently. But at the same time, if you want to get the same behavior, there are things to be done so that you get the same behavior. So there's always a way to get something to work. So if we show ls in this case will be 1 as one entity and 2 and 3 as another entity. And you can obviously add as many as you want. 2, 3, 4. So. Vectors are indexed starting with 1, unlike Python. You don't start indexing with 0. You also don't have negative indexing, but you have the keyword end to access the elements from the back of the vector. So vec of 1, if we're gonna see it here, it starts at the 1 vector because vec was 1, 2, 3, if you remember. And if you want to access the last 2 elements of vec, all you have to do is access vec of end and vec of end minus 1. So vec of end is 3, and before the last one is 2. And just to remind you of what vec was, this was vec. So you can go backwards. Now, what's going to happen if we do end minus 4, let's say? Any guesses? Yes, bounce error, because there's no negative indexing. We can only go end minus the length, but we can't go end minus more than the length. Actually, end minus the length plus 1. Okay. So types and functions. This is a very simple type. That's how we define it. If we want to define a circle by its x, y coordinates and the radius, we're going to define type as circle, you name it as you want, and then put your instances or put your fields of that type inside the type. You can decide on the type sub fields to have whatever type you want. So here we're deciding that they're going to be of type float, but in different cases we can say if you want to define type age, I guess age is not date, you're going to say day is equal, day is int 64 and month is int 64 and year is int 64. So this way we're defining another type, which is date, but it only can take input as integers. It can't take anything else. So just to give you an example, if I'm going to comment these out for a second, if we define date of say 10, 10.2, and 2.3, it's going to give me an error saying that this cannot be defined because these have to be integers. Here we're going to define a function on the type we just created, which is a circle. So we want to get the area of the circle. Say we have an input A, which is of type circle. This is how we get the area. Pi is a predefined value in Julia, so we can just immediately call pi. If we want to access r, which is the radius of the circle, we're going to call a.r squared, and that's what it's going to return. You can precede this by the return keyword, but you can choose not to as well. And here we define the function. Now we can actually call the function. Here's how we are defining a circle. The input is 10, 10, as in the coordinates are x, y, and r. And the get area function is going to take as input a. Now, I don't know if anyone observed this, but when we defined the circle, it only had types floats, right? But then we gave it integers to define it. So I guess it's obvious to you that if it's an integer, it's going to be casted to a float. But when we passed a float and we wanted it to be integer, it cannot be casted that way. So integer is implicitly understood that it's going to be casted to a float. So that's fine. That works, even if we pass integers. And that's how we created our first type, A, and we called a function on the type we created. This is a module, which is also similar to Python, if you agree. So this is a module. I'm calling it my module. We can define a type inside the module. So this is the type person, which has a name and an age. Name is of type ASCII string, which is really just a string. And age is of type integer. It has to be an integer. We also define functions on the type. So get name of person P, that's p.name, and get age of person P, that's p.age. If we want to be able to use these functions without preceding them with my module, so okay, I'm going to show you two things. I'm going to first try to comment this out and run the my module. And then I'm first going to create my module.person, created a person named Tia, whose age is 9. And then I wanted to get the age of this person P. To be able to get the age of this person, to be able to create the person and to call a function from that module, we had to precede both functions by the my module dot operation. There's a nice thing you can do, which is you can export these things. Export a person, export get name, and export get age. And now what you can do is okay. So what we did here is that we created a module, my module. We exported the functions in it, and then we preceded our code with this keyword using my module, which is telling the code, okay, I'm going to be using from now on anything that is in my module and is exported. I can be using these as just generic functions, as just functions that I defined. So all we had to do is precede this snippet of code by using my module, and then we were able to use these functions that were defined inside the module. Okay, any questions so far? Okay. We're going to move on to the fourth notebook in the first folder. These are things you can do in Julia, just also showing you more things you can do. This is A, defining A as, or declaring A as a value of 10. And then we are able to find the type of A by just calling this function type of A. So type of A is int64. You can always know the types of the things you're working on. B is 10.2. If you call type of B, that's float64. So you can see all these types. I think we saw something similar to this before. So you can set the big float precision. You can change any precision of any number you want by the number of bits you want to use to represent it. So set big float precision of 128, and then you can define C and D to be big floats of 2.1, meaning that you're using 128 bits to represent this value 2.1. And then you're saying, okay, there's this other value, E is equal to 2.1, and then now let's see the types and the types of C and E. So if we just show C by itself, you're going to see that it's slightly bigger than E, though they're the same internal value. If you see the type of C, it's a big float, whereas the type of E should be just a regular float. It's a float 64. And the fact that they're represented in different number of bits, that doesn't mean that this changes the value. C and E are still equal. They are still internally represented differently, that's right, but they have the same exact value, and the execution of C is doubly equal to E, which is a true or false operation, Boolean expression. It will be evaluated to true. This is how we define a vector of zeros. If you want 5 values, you're going to say, okay, let's define them by 5 values. Now you can notice that here I preceded this by the int64 value. If I remove this, the default is going to be a float. So this is a vector of 5 floats which have values 0.0. But if you know that your vector is if you know that the vector that you're going to be using in your code is always of integer types, you want to precede this 5 by an int64 to tell that this vector only has integers, and that's how you change it. The type has changed, as you can see. It's array of int64 now instead of it being array of float64. There are things that I don't know if you can get the impression so far, but you should probably be careful with types when you use them. So if you want integers, just tell the compiler you want integers. If you know you want floats, tell you want floats. So just kind of be careful with what types you're using. Here, for example, if you do 2 to the power minus 1, this is not going to work because to the power minus 1 will always return a double or a float 64, and 2 is an integer. What you should do for this to work is basically make this a 2.0. So something to the power negative has to be a double because this is a double operation. There are things, like the first time I saw this, I was like, oh wow, why is this happening? It's slightly annoying, but once you notice that types really matter, you start thinking that this is okay. You can use Greek letters. This is, I guess, a fun thing in Julia. So any favorite Greek letters? Anyone has a favorite Greek letter? Omega, okay. Do you want the small or the big one? Let's go big. So just capital OMEGA with a tab should translate this to an omega. So omega is equal to 10, and then you can say omega plus lambda, and that's going to be the value. So you can use these Greek letters. Again, being careful with types. If you have a vector v of type of values 1, 2, and 3, and you decide to change the value to be 2.5 in the first entry, you cannot do that. If v is equal to 1, 2, 3, it has to have types integers. So if you change this to 1.0, now you can change one of the values in v. So being careful with types is, again, important. The equal sign doesn't mean that you've created a new value or a new location in memory for the new operation or for the new variable you're using. So if you decide that v1 is equal to 1, 2, 3, and you say v2 is equal to v1, what this does is that it creates another pointer to the same data in memory. So if you say v2 is equal to v1 and then change the first value in v2, this will also change the first value in v1. So v1 gets changed. If you really want to get a copy of that vector, you have to use the copy keyword. And when you copy in this way and change the value and change the first value of v2 and make it 100, in that case, v1 stays untouched. It doesn't change any value. This is a simple for loop. This is how you can do it. You can do it, for example, here we're doing the same thing in two different ways. Every vector in Julia is iteratable. So by default, if you say for x in input vals, which is a syntax that is more similar to that of Python, you can access this x immediately by saying print line of this value x. If the input values are strings, it's going to be printing on every single line a different value of this string vector. If you want to go over each element by indices, you can do a for loop from the first element in the index till the last element in the vector, which is at index length of input vals. And in that case, you access the element inside the vector in this way. You access it by indexing its internal value. So these are just two different ways to do for loops. This is a simple if statement. As you see so far, all of the for loops or if statements have an end keyword at the end of them. This is one value. You cannot use ones and zeros as booleans. You can only use boolean values, which are true or false. So if this is true, if true, this works. If false, it doesn't work. But ones and zeros are really just integers. Their internal representation is an integer and is not a boolean value. This is a simple while loop. I guess there's nothing really very significant about this code except that just telling you, because before we go into more deeper stuff and you being confused with why is this happening, I'm just trying to tell you the things that are different from Python or showing you the basic syntax. If there's anything you want to ask about, please feel free to stop me. This is how you concatenate a string. If you have two strings, you concatenate them by the asterisk sign. So I concatenated the first string with a space and then concatenation with the second string. So that's how you do it. The last thing in this notebook is packages, and I guess that's really the most important, really the biggest thing in Julia, which is packages. In Julia, you can most of the things you want to do if you are like in a domain specific, if you want to work on a research in a certain area, you will probably go and try to find a package that suits you, a package that does some sort of, if you work in linear optimization, you're going to go and find an optimization package. If you really care about visualization, you will go and find visualization packages. There are plenty of them. As we will see towards the end of this talk, we will do packages that are related to statistics and machine learning, and we will do one package that has to do with data frames, and that will be a way to manage when you have data from a source file. I'm going to show you how you can use this package to manage your data. So the point here is that there are plenty of packages. The package for example, the package I'm using right now is iJulia. So I just used it here, and if we do using iJulia, which is the package I just added, now I'm using this package, and then I can create a notebook, and then this will open a Jupyter notebook for me to use. There are much more. This is how you can know what's the status of the packages you have installed on your computer. I guess if many of you installed Julia recently or just installed Julia, you will have very few packages installed, but I guess as you start using Julia more and more, you will have way more packages installed. If you want to update your packages, because these are things that are continuously being developed by by the people who implemented them, you can just write the package.update keyword or instruction. That's how you update all the packages on your computer. If you want to add a package, that's how you add it. I just showed you one example here. That's how we added package iJulia. If you want to remove a package, that's how you remove it. There are really so many packages on the Julia website that you can see. Depending on each person's interest, you can find ones that relate to your work. I don't know what's the major interest of everyone here, but I think there's one that we're gonna talk about towards the end, which is data frames. That will be very interesting. That has to do with managing and accessing data from text files, basically, and being able to do operations on them. But there are plenty more that I encourage you to look into. There's about 1,000 plus, 1,091 packages, and they're very well documented. Most of these, I don't think anyone writes a package without documenting it very well. And I guess I'm gonna show you a data range. It's the one we're gonna be using later on. So usually you can go and see the code of every package yourself. So if there's something that doesn't work, or you really want to dig deeper into what's going on, why is this failing, you can go into that package and find out why it's not working. All right, so this is about it for packages. Sparse matrices, I don't know how many of you deal with sparse matrices, but if you do know about sparse matrices, they are represented in not just a matrix form where we represent the zeros in it. We represent it usually either in a compressed sparse column format or a compressed sparse row or triplet format. But most people do prefer compressed sparse column or compressed sparse row. So Julia's representation is a compressed sparse column. So if we create a random matrix, a random sparse matrix of size 5 by 5 with a probability of 0.2 having non-zeros, this is a random matrix that will be generated. The really cool thing about sparse matrices here is that you can access all of these things like column pointer, you can get the column pointers. If you know the compressed sparse column representation, you get the column pointer, you can get the non-zero values, you can get the row values, and I guess this is all you need about a compressed sparse column matrix. This is the entire representation. And you can see it here. You can see the full version by calling the full of A. Is there a problem? Okay. Working? Okay. Exotic Julia and some performance tips. So these are things that are different in Julia, and I really like to put them out there in the very beginning so that people know that, again, you can't, if Julia is a choice for performance, we can't just, again, go write very generic Julia code and wait for it to be faster than another code. We have to take into consideration how Julia is implemented and how Julia is built. And these are some of the things that I show you here. To start with, for example, there's the vectorized versus devectorized. So vectorized operations are like sometimes faster, but devectorized operations, or for loops in specific, are very fast in Julia. If you want to do for loops, don't be afraid of doing a for loop on Julia. A for loop in Julia is actually, as I'll show you in 3 examples here, or maybe just pick one of these 3 examples, that for loops are faster than the vectorized counterparts of the operation. There's just one example that I'm going to show you here. For example, if we're trying to find delta, which is, if you remember from like middle school, I guess, if you have a quadratic equation, which is ax squared plus bx plus c, if you want to find delta, delta is b squared minus 4ac. So if you have the values b, a, and c, you can simply, by a vectorized operation, do b squared minus 4 times a times c. And that is the find delta vectorized function here. We really just did b squared minus 4 times a times c. That's all we did. The dot multiply means that we're multiplying element-wise these vectors. We're not doing a vector-vector multiplication. So a dot times c means that we took the first element of a, multiplied it by the first element of c, and that's how we got the vector. If we do the same thing by computing b squared minus 4ac while looping over the indices of the vectors, going from 1 to n, we will, and I guess, so this is the devectorized operation, which was almost 1 order of magnitude faster than the vectorized operation. And the reason this is happening is because in the vectorized operation, what's happening is that there's a computation that is happening. 4 is being multiplied by a, and that's creating one chunk of memory, and then it's being multiplied by c, and then that's creating another chunk of memory. And there's some overhead in communicating the memory, moving one item in memory to another place, and then putting all of these things back in one value and one chunk of memory. That overhead is taking some time. Whereas if you're doing the for loop, you're not dealing with any of that. You are literally just grabbing the first element, grabbing the first element, grabbing the first element, computing b squared minus 4ac, placing it in its corresponding value, doing it the second time for the second thing, third thing. So the for loop is not really an overhead in this case, and it's much faster. There are more examples of vectorized versus devectorized here. But I'll leave these for you for further experimentation. There's also an interesting thing, which is the const value. If you declare a const cannot change type. So if at the very beginning I defined something to be const type n, now I can do n is equal to 1000, const n is equal to 1000. I can say n is equal to 100, and it's just going to give me a warning saying, okay, we redefined a constant. But if we say 100.2, that's going to be wrong, because a constant value can change the value, but cannot change the type. So the compiler, once I've written n const n is equal to 1000, the compiler knows that this value is an integer, and in its internal representation, it's always going to be an integer. It doesn't care what the value is, it only cares that it's an integer. And if it's an integer, that's going to make things faster. So if in your code, for example, you know that there's something that is an index, it cannot be a double or it cannot be a float, it is always an integer, you might as well just define it as a constant at the very beginning. That way you're telling the compiler, do not change, this thing does not change type, so don't worry about it. I guess I'm going to try to stop in 10 minutes to give you a break, but there's one more things that we can see in this notebook. One of them is iterators. I think iterators is really fun because if you have a vector, or if you have basically anything and you just want to access it element by element and you don't want to worry about indices, it's really nice if you can just do for x in I, for example, for x in I, print, and then $x, let's say. Okay, I don't know what was happening earlier, but anyway, so if this is the vector, I just mentioned to you that every vector in Julia is iteratable by default. And the reason it is iteratable is that there are these three functions that are already defined on every vector. So you can see the start of I, which is usually the index and not the value. So start of I is usually 1, which is the first index. And then if you say next of I, 1, saying we were at the index 1 just last time, and now I want to find the second value of I, what's going to happen is that it's going to give me a new state, which is 2. So this was the previous state 1. This is the new state 2. And here it's going to give me the value. If I do this one more time, next of I, 2 or 3, it doesn't. We're going to see that we're going to get the values here in the first component, and we're going to get the states in the second component. The done operation will tell us if we have reached the end of the vector. So done of I at 2 is going to be false because this is not the last element of the vector. So what this means is that what's happening is that I is not changing. I is staying the same exact thing in memory, but we have these functions that are defined on it, which are start, next, and done. What this means is that if you create your own type, you can create an iterator with that type. All you have to do is define the start, next, and done function. Once you've defined start, next, and done, you're done. Your type is iteratable. And here we're going to see a simple case where we can do that. So here we're creating, okay, there are things more for you to see about iteratables, but I'm going to jump to creating our own iteratable object. So here we're going to create houses, let's say. We're going to create a type house that has the number of beds, that has baths, and square feet. So these are 3 things that are characterizing our houses. And then I'm going to define the 3 functions, start, next, and done. So you can see that I have preceded them with the keyword base, and that's because the default start function of Julia is located in the base repository. So any function that is in the base of Julia, base code of Julia, if we want to change it or upgrade it or add something to it, you can do that. If you want to change the plus operation, if you want to, I don't know, edit any function you think you want to edit it to take in types of your own types, you can do that. So all you have to do is precede it by base.start, or there's another way you can just export base and then just write start, but we can do this for now. So base.start of H being a collection of houses, that's going to be, we can define it to be 1, and then base.next of H being houses, and then taking the previous state. So we tell it what the previous state was, and we can return the next state, which was state, and h.bats of state, h.square feet of state, and then return state plus 1. Find that an iteratable is done by saying that it reached the length of that object. So here we're defining a collection of houses. The first house has 3 beds. So 3 beds, 2 bathrooms, and this is the square feet. 3 beds, 1 bath, the square feet, and so on. And now if we've defined these houses in this way, we can just for I and H, and it's just going to take it by default and be able to say, okay, this is how we're going to print these houses. So all you have to do is define start, next, done, and your object is iteratable. For example, Julia stores their numbers in column major and not row major. So if you have a matrix, they're stored in columns. We take the first column, it's stored first, and then the second column, and then the third column, and so on. Which means if you're iterating over a matrix, it's always better to iterate column-wise. Start with the first column, go access every element of the column, and then go to the next column and go on and so on. If you access things, if we are just doing pure iteration over entries in the matrix, if you really want to do that, it's always better to do it column-wise and not row-wise. And this is an example. If we're trying to find, if you're really just adding 1 to each element in the matrix, here we're looping over I from 1 to M, which means we're fixing the row I and then changing the column J, which means we're saying, okay, fix the row, go over 1 element column by column, and then fix the row, go 1 element column by column. So we're doing row major. This other case says we're doing column major, which means we're fixing the first column and then saying, okay, let's add 1 element to the first, second, blah, 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 and so on. So fix the first column and then go row by row, go to the second column and do row by row. And if these are doing the same exact things, and if we run these things, there's always at least 1 order of magnitude speed difference. If you do column-wise, it's always faster. You can do in-place operations in Julia. So if you want to change a vector, if you pass a vector v and you upgrade or you change the vector v inside the function, this changes outside the function. So let's say we are squaring in place. You do not want to create another vector v so that you can square this vector for it. This is how you do it. So you go over 1 through the length of v, square every element, and then return v. If you don't want to square it in place, you can create a new vector w and return your vector w. Yeah. Yeah, it's just a convention. So I hope it, sorry? Yeah, okay, yeah. The question, is this exclamation mark at the end of the function a convention? And the answer is yes. So with Julia, if you create a function that changes the input to that function, it's good. It's a really nice convention that people are doing is, okay, be careful. When you're using this function, it's changing the input. It's changing your input. Be careful. So like if I create a vector v3 equals to 3, 2, 5, 1, and then I do the sort in place of v3, which is a built-in Julia function, it's going to give me 1, 2, 3, and 5. And now if I do show v3, v3 has already changed. I can't access v3 anymore. It's changed forever. But there is another way we can sort, which is not in place, which keeps v3 as it is. So there's nothing special about this function except that it's telling the user, hey, be careful. When you use me, you're changing your input. You're never going to be able to access your input again. So if you write your own function and you want to change your input, it's always good to add this exclamation mark saying that the input is being changed. Okay, so there's really much more to cover here, but I really encourage you to go over the rest of this notebook in specific, because there are many things that, just like, for example, now I told you, if you do column-wise, it's always better. There are other things that you can learn from this notebook and be careful with while you're writing your Julia code. In specific, I guess you can always use the code warn type to check the code, the types of your functions. Okay, I guess I'm going to go over this one last example and then break. So here, for example, if you are summing a vector v, a vector vec, and you're going over all the elements in S and all the elements in vector and adding them to this value S, which is the sum of the function. There's a really cool thing that, so I'm not gonna, okay. So here we're just sanity checking that our sum function works and is equal to Julia's sum function. There's a really cool macro called code warn type, which tells you what's happening internally inside the code. So here, vector is of type array float 64, and here S is of type any. And whenever you have something in your code that is of type any, that slows down your code. Though S was defined to be initially a 0, right? Like we know it's a 0, but S initially could be anything because we're adding to it things. It could be a complex number, it could be we're adding something to a 0 and it's going to change its value. So the compiler doesn't really know what S is, but if you know what S is, it's always good to tell the compiler what S is. So the way to fix these things is just create a vector or create a 0 value, which is just 1 0 of the element type of the vector that is your input. I guess the take-home message here is that you can write generic and simple code, which is S is equal to 0, for example, but if you really care about how your code is performing, there are things that Julia allows you to do, like add code warn type. You can see the LLVM code. You can also see the machine code. So, for example, if you do here, so if you do add code native and do 1 + 1, you really see what's happening on the register level. So if you care about these things and you care about having a really fast code, you can just look at these things and say, oh, there's something wrong. There's this thing moving to a weird place. Let me try to find something in the code. And I guess there's this culture in the Julia, like whoever does Julia is like, first maybe you write your generic code and then you start using these code LLVM, code warn type. You start profiling your code and you see all of these things that is happening internally in the code and you say, oh, this is a generic S, it's of type any, then no, I know what the type of S should be. It should be the type of the input vector. So here, this is the example. Here, I said, okay, what's the element type? This is a function called element type of the vector vec. All I'm doing is creating a 0 of the type of the input vector. And when we do this and get the code warn type, I guess we didn't define it here, what happens is that S is automatically now known as a float. So you can see machine code, see more things. There are more things to see, like type stability. It's always good to return one type in a function. So if you have a function, it has to return the compiler. You can return different types if you want. If you want to return, if you want this function to return either or. Actually, I think I'll leave this example as the first thing to start with after we come back from the break. And there are more things for you here to go over. If you have any questions on them, we can talk over them about them after the break or after the talk. There's this very simple snapshot of what numbers are like in Julia, how they're represented. This is the generic number, and this is the tree, basically. If you can see what's under an integer and what's under a float. There's more. You can do multiple dispatch. You can define a function over different types. You can do functional programming. I think I'll go over a little bit of these things. One more example after the break, and then we'll do more statistics and machine learning stuff. I think we can break for 10 minutes and then try to be back after 10 minutes. Anyone has any questions so far? So right now, if we go back, we're going to use the third folder, which is wrappers and speed. In this folder, you're going to see that we're going to wrap a very simple Fibonacci function. I hope that everyone knows what a Fibonacci sequence is. So we're going to be doing the iterative version of Fibonacci. So there's the C++ version that I provide the code in the GitHub repo. There's a Python version and there's a Julia version. First of all, so the iteration is going to be based on this function x, y gets the value of y, and the new value of y is the previous value of y plus the previous value of x. This is the C++ code. If anyone has any objections, please stop me and say, hey, this is wrong, this is unfair, this is whatever you want to say. The Python code will look like this, and the Julia code will look like this. So I'm going to change the Julia code to be a little bit more readable. Okay. I guess my alignments weren't very, okay. I hate unaligned code. So if we have a function and we want to find the Fibonacci, the nth Fibonacci value of it, what we're going to do is, so here's where we define the function f, and here's where we're calling the function f. We started by defining f is equal to 0 because I want to run this function 10 times just so that we can time it in a better way, and then call the value f is equal to fib of 20 10 times basically, and we're timing this entire for loop, and here we're showing the value. So this is the Julia code. The Python code will be in a separate notebook. And I guess, and we can see that we're getting the same value. I'm not going to comment on timing because I know that these things might be a little unfair. I don't know if there's different timing package that people prefer to use, or I know that with timing it's always tricky. But so these are not real benchmarks. I don't intend them to be so. I just put the timings there for fun. These are the simplest ways we could time things. But please feel free, if you want to benchmark these things, you can do that yourselves. The C++ code is also provided in the GitHub repo. So if we do cd, okay, so G++. So we're compiling the code, and then 20 is the value. So the iterative function gives us a 6765, which is the same value, and this is the elapsed time. Okay, now we have a C++ function, we have a Python function. Is there a way to call them from Julia? This is the question. And now we're going to do the C++ version first, and then do the Python version first. All we have to do here is add this extern C keyword to the C++ codes, just so that we tell the compiler that there is a C linking happening. It's not a C++ linkage. And in that way, if we add the extern C keyword, that's going to tell the compiler that this is that this is C linkage. Once we've created this, we're going to create a simple makefile that will literally just do compilation of the code and create a shared library. Now, I really don't want to go over the details of, like, some people might know how to make makefiles, some people might not, but this makefile is really specifically simple. What it's doing is really just 2 lines. First of all, compiling the code. So compiling the code with some flags that we decide them to be here. I'm not going to go over them, but some people might know what they are already. And the second thing that's happening, the really difference here, is that we're creating this shared object. We're creating, if it's on a Mac, let's say, it's going to be a dynamic library. It's going to have an extension dylib, And if it's on a different system, it's going to be a .so, so shared object. And this is, so if you're running it on whatever machine, I think it should still work, because in the make file, it already has, it knows if it's Linux, it's going to be so shared, and if it's going to be a Mac, it's going to be a dynamic library. So you should be fine. So now if we go here and make this function, we're going to see that we have created something new called fiboextern.c.dylib. So we created this dynamic library. And again, just so that you know, the code was really just this simple function. So extern c, this was the code. So it was so if you want to look at it on your GitHub repo, it's fibo_extern_c.c++. After we have it, now we can just go to Julia and just call it. We have a shared object. It's really simple. To be able to know where the shared object is, because it could be an SO or it could be a dynamic library, and because we want to create as generic code as possible, what I do here is that if the OS name, which is already something that Julia realizes, or it's a reserved keyword, if it's Linux, we're going to append to the current working directory a file called fibo_extern_c.so, and if it's another thing, it's going to be dynamic library, and it's going to append this thing. And now you have the library path, on whatever system you're working on. And now you can call this function called ccall, which takes as input the function name, which happens to be Fibonacci_I in my case. So if we open fibo_extern_c.c++, well, this is very small, but this is the function. It's Fibonacci_I. So this is the function name. So here's the function name. The lib path is what we just defined up here. So function plus library path. This is the return type. So we notice here that the return type is an integer. It could be an int. It doesn't have to be int64_t, but it could be an integer. So it returns int64. This is the input. So input type. So the input type is also an integer. So we tell it what's the type. And then the last thing is the real thing we want to find, which is the value n, which was passed to this function as input. Now, this is the syntax of the ccall function. Once we've created these things, we can define this new function called C++ wrapped fibo that is really just running C++ code. And now if we want to run Julia code, all we have to call is the C++ wrapped fibo on 20. Now you have a Julia function that internally calls a C++ function, or specifically a C function because it's been linked as a C function, which didn't work because I didn't define. Oh, I know what's happening. I guess I'm in a different directory, so. Okay. So I am in the correct directory. Okay, it works. I guess previously the directory wasn't, I probably had missed a slash or maybe just didn't run it. I think I didn't execute this cell. Okay, so what we did here is that we got the path of the library. We created this function using the ccall function, function name, path, return type, input type, and the actual input, and we returned the value R. And now we can call a Julia function that wraps a C++ or a C function. The Python wrapper is even simpler. So this is the Python code that is exactly the same thing as the one used in the Python notebook. So if we run this thing, okay, this was here, what's going to happen is that we're going to use, just as I told you, there are packages, and packages are really the building blocks of Julia. Here we're using a package called pycall. So pycall lets you do whatever you do in Julia, you can call it using this pycall function. There are so many things that are still, they're working on them, and they're probably going to get better soon, but so far, I guess it's a very, very, very nice package. I guess it's one of the most popular packages because you can take Python code as it is, just compile it, just pass it as a function name to a Julia function, and now you can use your Python code as Julia code. This is the Fibonacci code again here. And there's one thing with the pycall, which is it doesn't search in the local directory for your module. So I guess this is going to be fixed at some point, but so far you can use this small hack, which tells the code, okay, you can search in the local directory where we are. So using pycall to use the package and unshift this searching for directories will be here. And then next, all what we have to do is use this macro at pyimport. Edit. So fibo.py is really just this, defining this fibo iteration function that is in the Python code. All we did is importing it, and now we can call any function that was in fibo as just another function. So pyimport, call fibo.fibo fibiter, you're done. You're as if using the Python function just as a Julia function. You can really define more things, like if anyone wants to define something just for fun. A global variable inside here, outside. I guess. Let's find out. So you have to re-import it because you've changed it. And then so no, I think you can't access global variables, but if you have the functions, you can change those functions. Yeah, there could be. I could be wrong, to be very honest. I'm not absolutely sure. I have never used a global variable from Python to Julia, but there could be a way. If it's not standard, I guess there could be a hack or something. Okay, so that's how you do it. You just call it preceded by the module name and then the function name. Great. Okay, any questions so far? Sorry. Okay, so in the Python code. Oh, okay. Just type X. Okay. Oh no, it's not gonna work that way. But yeah. So what did you want to try here? No, it's not gonna work that way. No. Usually there's another Python package wrapping in the fourth folder. So if you want to see a more complicated wrapper, you can go there and see it. But there's one interesting thing, which is if you want to access a subfield of a variable in Python, If you want to do it in Julia, you have to use the colon keyword or the colon convention. This is just a very small. So I guess here I just imported a Python, a standard Python package, and I'm calling this function from it. It creates a Py object. What I'm trying to show here is that at some point, if you want to access a function of this Py object, so again, gvx is a Py object. If you want to use a function on it, since the convention in Julia is that dot function is something else in Julia is defined differently, so they decided to define it in a different way, and if you want to use a function, you have to use this convention. That's the only difference. But in terms of global variables, I'm not sure how you could do that or if you can do that. Okay. So as I mentioned, I'm not going to go over this fourth folder, which is wrapping more complicated C and Python code, but I encourage you to go into it and find out how, if you just go online and find a C package, you say, okay, I want to use it in Julia. Is there a way? There is a way. If you go online and find a Python package that is very well established and you don't want to rewrite the entire thing in Julia, is there a way to wrap it? There is a way. And these two examples in the fourth folder can walk you through this process. Okay, the fifth folder is data frames. So first I'm gonna go over basic stuff that any person working with data would be interested in. So here, for example, if you create a random vector of size 100, you would probably want or be interested in finding the mean of x, standard deviation, or variance. So these are functions that are in the base code of Julia. There's this other package called statspace that has really more interesting or a very big variety of statistics equations or statistics functions that you could use. So we can call it this way. If it's your first time calling it, you have to use package.add statspace to be able to use it. And now this gives you some functions that are more interesting. So if you do describe of x, you can get the mean, minimum, first quartile, median, third quartile, and maximum in just one keyword. You can get the geometric mean, for example. You can get the z-score if you have x, so x minus mu over standard deviation. So these are just basic stuff that people might be interested in seeing. This is the data frames example. I told you that we're going to use data frames later in this presentation to show how you can access data that is already written in text files. So here we're going to use two packages, data frames to be able to manage data, and our data sets will be our package. It has a lot of existing data sets, so maybe we want to play around with one of their data sets. That's why I'm using it here, because later on I'm gonna call one of their data sets. So here we're telling Julia that we're gonna be using these functions. There's a really cool thing about data frames, which is it introduces the NA value. So many of our data sometimes doesn't have values all the time. Sometimes you just have missing values. So you might be confused, do I put zeros there? Do I put minus ones? What do I put? In data frames, there's a really nice way to do it, which is you just put an NA. So if you define A to be an NA, what happens is that if you add a number to it, this new number is also an NA. It's not a number or doesn't exist. The type of A has a new type. So data frames created a new type for Julia. So if you want to use that NA, it's really just a new type. And they defined all these, like the plus function. So the plus usually didn't operate on an NA, but the data frames package defined a plus on an NA and said, if a plus is being operated over an NA, let's return an NA. This is a simple data array. If we have a set of states, let's say, the first state is we don't know it, but we have 3 other states that we know. We can get the type of this array. What It's an array of ASCII strings. They're strings, except that the first one is an NA value, so it doesn't have a value. You can do the same thing with numbers. Instead of strings, it could be numbers. Well, it could be also strings here. So it's just a data array. It's an array of things. Except that if you noticed when I added test, so there was no any keyword before it because it knew it was integers and this NA thing. But now when I added test, which is a different type, it now knows that this vector could be of any type. It can have many different things inside of it. We can get the mean of these numbers, but since numbers, let me just redefine numbers as numbers because we're going to use that later on. You can get the mean of these numbers, but since it has one NA value, it's going to give you an NA, but there are things to get away with that. There's the drop NA function, for example. What it does is that it just assumes that this value doesn't exist and creates, and if you want to find the mean of it, you can just do mean of drop NA of whatever data you have. The other thing you could do is sometimes you don't want to just drop your NA. So let's say you're trying to compute the mean and you really want to divide over the total number of elements. You don't want to divide over the total number of elements that have value. What you can do is convert your numbers, which is a data array, to a regular array. And then what this extra element here does is that it tells, the function is saying, whatever value has an NA value, let's switch it to a 0. So the conversion here could be anything, like we could do a -2, or we could do just any value you would want to see. So you can convert any data array to an array, given that you tell it what to replace NAs with. So if we don't tell it what to replace NAs with, it's not going to know. It's going to just give us an error. Though if it didn't have this issue, it won't complain about transforming. It won't complain about transforming a data array to an array because it already knows the values. But an array has to have all the values should be non-NAs. Complete again. So I'm gonna convert every NA to a 0. And now you can get probably different averages if you're interested in different averages. You can reshape these things. So if numbers was a 4x1 data array, you can create a new data array which is of size 2x2, let's say. So there's a reshape function defined on it. You can multiply things by each other, even if they have NAs. So if you have numbers reshaped as NA2 in the first row and then 1, 3, if you want to do a matrix multiplication on these things, it's going to just show you NA, 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 and then 11 because the 2, 2 element was the only valid element to be computed. All the other elements had involved an NA multiplication, which is not valid or will give an NA value. This is a very basic data frame if you want to create it. So you can say these are the names of the people and these are the ages, let's say. And then you say, here's a data frame that consists of the first field. You're deciding the field name here. It's called names is equal to this vector n. And then you're defining the second field to be ages, which is equal to this vector a. And then you can show your data frame. So your data frame gives you the number of rows as the first column by default. These are the names and these are the ages. If we defined anything else, it's just going to be different. So it's going to be capital names. Whatever you want to find, whatever you want to name this column, you can name it in this manner. The other thing you could do is, so for example, this is another data frame that is based on also names. I'm going to switch back to. This one is also based on names, but also based on income as well. So if we create this data frame, we can join this second data frame, which is based on names and income, with the first data frame, which is based on names and ages. with this very simple keyword, which is join. So we're joining df, which is the first data frame, and dff, which is the second data frame. And then here we're saying join them on names. And names is the name of the vector or the field that we're basing everything on. What we could do, so here you're going to see that this will create a new data frame that is combining both of the things. But what you could do as well, okay, sorry. Okay. You can access the columns by either accessing the field name, which is names in this case, or the index of the column. So df of 1 and df of names is the same exact thing. They both show the names. You can also describe an entire data frame. So if you describe a data frame, you get a description of the first field, which is names. It tells you some information you might be interested in. Since ages is a numeric column, you will get some other values like minimum, maximum, median, third quartile, first quartile. Okay, so this is very basic data frames that you can create, or things you can create from your own, if you want to just experiment with data frames. Now, most of the cases you already have your data set and you want to import that data set. So here are cases where you would import these data sets. So here we're calling this function dataset that belongs to this package called our datasets. But since we're using our datasets, we already know that we can call this function. Okay, and we're calling the iris dataset. So here's how it was created. You can see it here. And now we can do more things on these on this data. For example, we can get statistics on each column. So let's say we want to get statistics per species. In this specific case, we have 3 species. Well, I didn't really count them. I just knew they are 3 species because I decided to filter them based on species, and I decided to apply a function on these things. So what was the function? I said, okay, group every species by itself. So go get all the species that are setosa. So get those things together. Go put them abstractly if you want. Go put them in another table and then go apply this new function on them. What is this function? Take the petal length column and find its mean. So it's as if we truncated this big data frame into just sesota data frame, everything that has sesota in its column, but it still has all the other columns. So now we said, take this new data frame, get me the mean of that specific column, which is petal length in this case. This could be any other thing. It could be, I don't know, petal width. So this is the mean of the petal width. And there's also, what you could do is just get the size of TF. So this will tell you how many elements did you have. So the size of this DF was 50 by 5. Sorry? Yes, you can rename the column. Can't remember exactly. I guess there's one example where we rename the columns in a second. Okay, so there are more functions you could use. So mean of this column, iris of dataset, median. You can get the head. The head is by default the first 6 rows of the data frame. You can also do column-wise operations. So, okay, let me just actually take this one step at a time. So here you got the mean and median. And I'm going to comment these out, just create more space. Okay. So the really interesting thing with column-wise is this entire data frame is not really a matrix. So usually if you have a matrix A, which is equal to rand of 5 by 5, you can just do mean of A. So mean of A comma 2, what it's going to do is go over each of the columns and find the mean of these columns. But in this case, you can't do, I mean, I said, okay, I'm going to do mean of iris comma 2. It's not going to accept that because this thing is a data frame. So it's really nice that you can go do column-wise operations. So whatever function you want to apply on a column-wise, on each of the columns of the data set, you can just call this column-wise function and put the function here and put your data set here. The reason we're passing just the first 1 through 4 columns is because the last column is not really a numerical column, it's just strings. So actually, out of curiosity, we can see what happens here. Median doesn't work on strings, so it's going to complain. So we're going to just go 1 through 4. Okay, so this is one public data set that we used from our data sets. Now what happens if we want to use a CSV file that we already have? There's a really nice function called read table that automatically reads any table you want. It has different formats if it's a CSV or tab separated, or there are many different formats, but this is one of them, the most famous CSV. So automatically, if you read the table, get it here. I guess I'm gonna, okay, so this is how you write a table to a CSV file. So if you have already created your data, just like we did 1 second or a few minutes ago, so this is your data frame, you can easily write this data frame by this write table function. So you've already defined this to be df, so you pass df as the second input, and the first input is the file you want, and you now have your data written to a CSV file automatically. Okay, this is more examples. So okay, I'm gonna do the last example first and then go back to the fourth if we have the time. Okay, it's gonna take a little bit of time. Okay, fine. So I'm still going in order. This is the third Python notebook, sorry for the confusion. So these are the packages that I'm gonna be using. I'm writing them here because, like, as you will see later on in this notebook, I use a certain function from one package. So instead of writing the using package keyword inside the notebook, I just prefer to put all of them at the top and then go on. So here is how you can read data from a URL. So if we have this URL, we can define it just as a string. And then there's a read table of this function as part of the requests package. So you go get a request, URL request, and with that, you read your data, which should hopefully work if the internet is good. Okay, great. So it's the same data set that I had already saved on my computer, but this is now getting it from the internet. Now we're going to be doing some plotting. So if we have x if we get x as the square feet of the houses and we get the prices and we want to plot these things, here I'm going to use there are multiple plotting packages, and if you are really interested in finding good ways to visualize data, there are so many resources online. I don't want to go into visualizing here, but this is just one way to visualize. I'm using this pyplot function, which you can tell is actually a derivative from a Python package. And once we plot, sorry, this usually doesn't take that long, but I guess my computer is not very cooperative now. Okay, I think I'll stop running these things. I'll just show you the result as they are. What happened when I execute this thing? So when we executed this thing, there was a problem, which is we saw as many of sometimes the data is missing something or has some values that aren't meaningless. So here we were plotting x as the square feet versus y as the price. So we realized that there are so many houses that have 0 square feet that were very, very pricey. So this was obviously wrong. It can't be of 0 square feet and has a very high price. So what we can do is filter things. So we go get the houses that have square feet that are bigger than 0. And we can filter those very easily by just this keyword. We can just get the square feet, whatever is bigger than 0, get those, and then we have this will give us the indices of these things that have bigger than 0 square feet, and this houses will just tell us, okay, based on these indices, let's pick those instances of this data set and just plot these things. Now, after we filter the houses, we can plot them again using the same x and y being square feet and price, and we will see that we got rid of all these 0 values. We can also get the size, as we saw before. We can get more things like the mean or whatever function you prefer. And now we're going to do some k-means analysis on this data set. So if you have this data set and we get just the latitude and the longitude of these data, so they're the x, y coordinates, you can think of them as this way. And then if we transform this data set as from a data frame, because x here is a data frame, if we transform this data frame to a just regular array, which is of size of number of houses by 2, so the reason we're doing this is because we want to pass them as to the k-means function, and the k-means function takes instances, which is the number of objects we have versus the number of features we have. So we have those as a matrix, and it requires this to be an array. And k is usually the number of clusters we want to cluster these things into. So you can see that we can transform or convert the data frame into a new data frame. Into a new array. And then there's the code is, what's happening here is that really after we did the clustering, we just want to plot these clusters. And what happens here is kind of interesting just to see what neighborhoods cluster together. So we can see that this neighborhood is really very, very distant from everything else. There's this neighborhood, there are other neighborhoods. This is just to show you that these houses, they already had latitude and longitude, but they also had a zip code. So here I'm clustering them. Sorry, I'm not clustering them. I'm just coloring them based on their zip codes. And I'm just showing you that this clustering was very similar in a way or another to this zip clustering. So which means that the zip codes that are distributed over houses, probably there's something about them being obviously close to each other. And I'm just validating this by a k-means clustering, which is a statistical model, and then by using the zip code, which is a pre-known model. All right, so I guess I have 10 more minutes, so I'll try to pick. Actually, for the last 10 minutes, does anyone have questions before? Yeah. Mm-hmm. Good question. Great question. Okay, so the question is, I understand we can do all of these things in Julia. Why would I want to do these things in Julia and not Python, let's say, right? Okay, so I guess my favorite answer and my personal answer to this and why I use Julia in my personal research is the following. So far, if you have an idea, let's say, and you want to apply it on some data set and say you come up with a new way to solve a real world problem, some problem in this real world and you want to solve it. What happens most of the times, and based on my personal experience and what I've seen so far, is that you go and try it with either Python, MATLAB, or R, and just see if the idea works. Run it on a couple of data sets, run it again, tweak things, change things, and then, okay, my idea works. What happens next in most cases is that you go and implement it in C or C++ so that you get performance. So this is what the Julia folks are trying to get away from. If I have an idea, why don't I just implement it in Julia and get the performance as close as possible to C? And that's happening in most cases. Like my first experience with Julia was creating 1 billion edge graph, and the only way it was possible was through a C++ code, which was really, really very painful. And the C++ code is just only like, I guess, less than an hour faster than than the Julia code. And I'm talking about generating this 1 billion graph took about 4 hours, and Julia took about 3.5 hours in C++. So I guess if I'm writing easy code, I'm fine losing a half hour for a really good, fast code writing. Lines of code is way less than the lines of code of C. Sure. Other questions? Mm-hmm. So the thing is, Julia, again, is a very new language. It's 3 or 4 year old language, right? So you can't request from people who have decades of very well written and documented code to tell them, hey, let's just go convert everything to Julia, right? So if you have the reason I made sure to show these wrappers thing is because if you have this entire repository of code that you've written over the past 10 years, let's say, what you can do is there are easy tools that you can use them to wrap them into Julia. But obviously, if you have the time to write them in Julia, that's like, you are encouraged to do that. And if you are, like for me specifically, if I'm writing new research ideas or research code, I'm starting from plain Julia code because I know it's going to be faster eventually, so why not start with it? So that's the morale behind it, if you want. I guess better is like a very, very big. Sorry. Oh yeah, sorry. The question was, is Julia better for scientific computing? Is that the question? Yeah. I guess better is like a really, really, really big word. Who am I to say that one language is better than another language? But I can say just based on personal experience, I've experimented with Julia, I've experimented with MATLAB, and I've experimented with Python. And my personal experience is that these 3 languages are user-friendly in terms of syntax, but Julia is almost always outperforming them. Sorry, I can't hear you. No, it's okay. So the question is it because of the number of floating point decimals or something like that? It's really because the Julia code gets compiled to machine code. So like you can see what's happening in the register level. You can see what every single thing that's happening on like what memory is being moved and everything. So you can write this code keeping in mind that you can see all these. You can use all of these tools to profile your code and analyze your code. So it does get compiled to machine level code. So it's not an interpreted language. So yes. Yeah. Can you repeat your question? Not right now, maybe later on. So, okay, the question is, can you compile Julia to an executable? And I said, not right now, maybe at some point. But, I mean, it's, again, a very young language. So if you choose it, sometimes you have to keep in mind that there are things that are not as mature as another language. But, again, based on personal experience, I've never really faced a situation where, oh, I need this function and I can't find it. Like, almost always all the functions are there. So, and worst case scenario, if the function is not there, the writing code in Julia is simple, so you can write it yourself. So, other questions? Sure. Oh, there's a very big thread about that. You can go read so many blogs about this. I guess I don't know, I really can't defend either or case. Well, I mean, I don't know. I don't think I can answer this question. But yeah, there are so many people that are with or against the one indexing. Yeah, I don't know. Other questions? Okay, before I end, I'm just gonna tell you what I'm leaving you with. This last folder that was about machine learning was really about using these statistics functions that are existent in the base Julia code or the statistics packages. And there's this data frames package that has to do with importing and exporting data frames as from text files and being able to manipulate them and run some functions on them. The last folder had this. The third example, we only did the k-means, but there's also a k and n example that you can see. And the fourth notebook has a regression model. If any of you knows about regression or linear regression, is really just a bunch of mathematical equations that you implement. That's a very basic example. And the fifth one, which I was hoping to go over, is really just here. I'm just showing very basic machine learning things that you could use, like k-means is one of them. If you have this data set of iris, if you want to plot it and get the colors of each cluster clustered in front of you. You can do PCA, which means that you basically shift or rotate your coordinate system or also shift it, get the new coordinate system. This is the same data set that was plotted up here, but with PCA applied on it. And I guess these are two of the things, k-means and PCA, but there are more functions that you would want to play around with. Yep. Mm-hmm. Yeah. So there's so if you so the question is there a testing package? So usually if you write your own package, let's say for Julia, you have to pass certain tests. Like you have to have your own test folder that has all of your tests. And there is another package that usually checks for all of like warnings in your code, or like if you want if there are errors in your code. It's called lint, and usually every package that gets published, they usually just go through a lint check before they publish it. Mm-hmm. That's it. Okay, I guess if you have more questions or if you want to talk more about Julia, I guess this was our outline. These are some more resources, just a few. That this PDF is also on the GitHub repo, so you can use it to go to certain links, Stack Overflow, Google+, and there are some more tools. And if you want to reach out to me, I'm almost available on Twitter and GitHub or any other social network except Facebook with this same exact handle, Nassar Huda, so you can find me anywhere and ask me any question. Except Facebook, not because I don't want you to reach me on Facebook. I'm not on Facebook, that's the reason. Okay, I guess that's it. Thank you.